Okay, today we discuss normal error regression. It's quite a bit long. So we'll try to cover the entire number of slides today. So this is, so why normal error term? So least squares method provides unbiased point estimator. So we discussed that last time, why we use least squares estimators for estimating beta naught and beta 1. And also they have minimum variance among all unbiased linear estimators. So proof you can do later. I won't be questioning any proof at the exam. So you can do all of them as an exercise, but proofs are important. Just I'll tell you at the time. So the form of distribution of error, EI, epsilon I is the error, is needed to set up interval estimates to make tests, hypothesis testing of regression parameters. Of course, it is very important. It is one of the main assumptions in regression. So if error is not normally distributed, it's going to be problematic. Basically in hypothesis testing, we goes with this major assumption. It is assumed that error terms are normally distributed. And for normal error regression, this is the model. If you're asked to write the model, you have to write this entire slide. So this is basically the same regression model that we discussed before, where yi, value of response variables in the ith trial, you simply can say ith response. Beta naught and beta 1 are the model parameters or regression parameters. You call them by different names. This is basically the intercept and this is the slope parameter. So you know which is connected to x is going to be the slope parameter. Xi is the known constant. We take x as a constant, although it is a variable. We consider the model at each x level. So it is a constant. Value of the predictor variable in the ith trial. Epsilon I is the random error term such that identical and independent and identically distributed. In short, you can say IID, independent, identically distributed, which means all the error terms that you find here are independent of each other. There's no dependency at all. Identically distributed means the distributional form of the error is identical. Identical means exactly the same, right? So it should have a mean of 0 and some constant variance. So whenever you are asked to write the regression model, you have to write the things up to here. If at least one of these is missing, you're going to lose marks. So make sure you write everything. You have to define this in every term, and you have to give the assumption of the error term as well. Next one is the normality assumption of the error is justifiable since the error term represents the effects of factors omitted from the model that affect the response to some extent and that vary at random without reference to the variable x. So why do we give a common distribution to all the errors without specifying at each x level? This is the reason. Normality assumption of error is justifiable, right? Errors represent the effects of the factors omitted from the model. So error is basically what? The gap between the fitted value and the estimated value. So it is spoken to the entire model, not at each x level, just as the response variable. We call the response variable upon each level, each x level, right? But for errors, we can generally say errors should be normally distributed to the entire data set. The regression model implies that this happens. Of course, you know, in this one, if we take the expected value both the sides, so expected value of yi or yi hat is going to be expected value of this one, and as these are unbiased estimators, we still can write it like this. And it has a constant variance. So expected value of error is going to be 0. That is why it says like this. Error, we expect the error to be 0. Error is not 0, right? If the error is 0, it's going to be overfitted. But we let the error get very close to zero. What we try to is minimize the error, not to make it zero, but minimize the error. If you want to make the error zero, you have to overfit the model, which is not going to work in this case. So expected value, we expect our error to be zero. That is what it means. So expected value of error becomes zero. So this is going to be the mean. Basically, yi is distributed as with this mean and a constant variance. The variance should be constant at each x level. Always yi is spoken in terms of x level, yi given x. That is how it is usually meant. Right, so I told you that these could be estimated by using maximum likelihood, which you already know how to do that. So this is just a recall of how you estimate parameters using maximum likelihood. Right, what we use so far is was the least squares estimates or the ordinary least squares estimates, OLS estimates. You would be getting the same result when you come up with MLEs as well. So let's see how we are going to do that. We are not going to work out anything. Everything is there in the slide. So this is the model. Since error is, so please put an N here. It should be normal. Normally distributed with mean zero and variance sigma squared. Please put a capital N here in your notes. Since error is normal with zero and sigma squared, what is the distribution of E? Normal distribution. So this is basically the probability density function of this. If this is normally distributed, this is the PDF of that. So since the mean is zero, negative half over sigma squared. Here you have the term xi minus mu whole thing squared. But here the mean is zero. That is why we have xi squared. In our case, our random variable is error, not x, right? It can be any letter. It doesn't have to be x all the time. You can denote your random variable by any letter. So in this one, just like fx, you have f epsilon I, right? Just like fyy, you can have plug in any random variable here. So instead of x, you have this here. Just because the mean is zero, for the PDF of a normal distribution, you have substituted that value, and this is basically the PDF of a standard normal distribution, I should say. Not standard normal mean, but variance is different. If standard normal, it should be mean zero and variance one. Here the variance is constant, so you can't put one here. It's just sigma squared. So if you know the PDF of the distribution, then of the random variable, what are you going to do as maximum likelihood first step? You are going to get the joint distribution for all the observations that you have in your data set. Okay, so the likelihood function is this. We have three parameters here in this case: beta naught, beta 1, and sigma squared. All those are parameters. Mean is known to be zero. For n number of observations, so let's say we have n observations, we have n data readings, so we have n number of errors, fitted value and the gap between the fitted value and the actual value. So we have n number of errors, right? So we have to get the product. So this is the definition of maximum likelihood estimation. We start from here. If you can't remember, just recall. You get the product for over all the number of observations that you have. You put the PDF here, right? And this is the variable, actually, the error term. So you substitute this part on behalf of error. You can isolate error term. So yi is equal to beta naught plus beta 1 xi plus error. So when you isolate error, it's becoming this. You substitute that because you are interested in estimating not the error, but beta naught, beta 1, and sigma squared. So you have to write this error term in terms of betas. That is what basically done here. In maximum likelihood estimation, we do not go to maximize the likelihood function, but the log likelihood function. You all have learned this in your second year, right, for the inference mathematical statistics 2 course under inference, and under point estimators you have learned this. So the log likelihood we denote it by simple L. These are the parameters of interest. And so this product becomes the summation. You just have to take the log of this. So log of this both sides. So when you simplify that, you are getting a statement like this. The parameter estimates of beta naught, beta 1, and sigma squared can be obtained by taking the partial derivatives of the log likelihood. So to find a maximum or a minimum, what you should do? You get the derivative and equate it to 0. Then only you are getting a turning point, right? You all are math students, you know this. With respect to beta naught, beta 1, and sigma squared, you get the partial derivatives. And setting each of the partials to 0, right? So you call these the normal equations. So here the log likelihood function is differentiated partially by beta naught, here by beta 1, here by sigma squared. When partial differentiation comes to the story, if you differentiate it with respect to beta naught, everything else is going to be considered as constants. So assuming that you have come up with this, and whenever you equate it to 0, it's better to put hat signs here. So those are missing. You can have this statement. So when beta naught is equal to beta naught hat, beta 1 is equal to beta 1 hat, and sigma squared is equal to sigma squared hat, the entire equation is going to be equal to 0. So please make that adjustment there. It's better, people write like this, but it's better to put the hat here, 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 and in all the equations. Please. Then you have to do your math, and these are the outcomes. So these are the maximum likelihood estimates of beta naught hat, beta 1 hat, and this sigma squared hat. So anyway, we are using OLS estimates in regression. So just because you all know what maximum likelihood estimation is and how it is done, I thought of including this part here. And properties of these, of course, ML estimates of beta naught and beta 1 are the same as least squares. By looking at this, you can see, right? They have the properties of all least squares estimators. So they are unbiased. They have the minimum variance among all the unbiased estimators. So that is why they have a minimum variability. In addition, ML estimates are consistent and sufficient. So you don't have to do the proof even later. This is very advanced. These are discussed under advanced statistical inference courses. So this is not going to be covered within this course. Consistent means when you increase the number of observations, the limit distribution of MSE, mean squared error, converges to 0. That is the basic idea. So better, it's better when you increase the number of observation all the times, and the error, mean squared error, gets very close to 0. When you keep on increasing the sample size, if that happens, we call it a consistent estimator. So you all have discussed this before in previous courses. So these are just the properties of ML estimators. And yeah, so we are going to look at some more properties. So let's take beta 1 hat. It is basically this. So we can write it as a linear combination of yi. So this summation ki means this, right? If we let ki to be this part, we can see it is a linear combination of yi. So hence beta 1 hat is a linear combination of yi, where coefficients are solely a function of the fixed x level. So when you fix a particular x level, when you fix it, this is going to be a constant, right? xi is going to be a constant if you fix. X1 is just x1. So at a given x level, this is going to be a constant. So that is how you say beta 1 hat can be written as a linear combination of yi. We'll see where we are going to make use of these. So this is the derivation sort of, and you have some other properties of ki. So you have to know ki is this quantity. You have to study that. And the coefficients of ki has the following properties. So if you take summation on all the observations of ki, that is going to be equal to 0, just like the error terms. Summation of this quantity is going to be 0. Then if you take this quantity, ki times xi equal to 1. So I have omitted all the proofs because it is highly theoretical. We are doing applied mathematics. So I didn't think of including the proofs. So if you're interested, you can try to prove this. You're given the form of ki, so you can use a couple of techniques and prove this. It's easy to prove this. But since this is an applied course, I really didn't think of including much proofs, because we have a lot of theoretical, practical parts to discuss, which is going to be very essential in your research. So I am focused onto that. But anyway, we cannot omit these things. These things are there in the course. If you take squared sum of ki's, it is going to be equal to this. Still, this is provable. So I'm not telling you not to worry about these much. Anyway, don't worry, but just as an exercise, try to come up with proofs. I'm not going to test these things at your exam, but as an exercise, do it. It's a good brain exercise. Then you would be able to get thorough with statistical concepts. You will understand things when you are doing this, right? So I'm encouraging you to prove, but it's not tested. Linear function of normal random variable. So if y is a normal random variable, if y is basically normally distributed, the transformed variable y equals a plus cy. So it is again y, some sort of a transformation. They have added a constant term and they have multiplied this, they have weighted this y, okay? So a and c are constants, is also normally distributed with mean this one and variance this one. So this is a very common statistical theorem. If a random variable is normally distributed, the linear transformation of that variable is also going to be normally distributed, and it has a particular mean and a variance. How do you get the mean? Expected value of this is equal to expected value of this. So you know expected value of a constant is that constant itself. So you can take the constant term out of the expectation. So it's going to be c times expected value of y. So y is normally distributed with some mean and some variance. So that mean is coming here basically. Expected value of a random variable is the mean. So you multiply the mean by the constant and you add this constant. So that is going to be your new mean of y dash. And variance of a constant is 0. So this a term cancels out when we are getting the variance of y dash. When there is a constant multiplied with the random variable, if you take the constant term out of the variance, it is going to be squared. So these are very basic things you might have forgotten sometimes. I just had this slide included here just to make you recall all those. Right. Then we are discussing sampling distribution of beta 1. You might be thinking why I'm discussing all this. We are going to make use of these at the end, because without knowing the distribution, how can we make a confidence interval? Without knowing the distribution, how can we do a hypothesis test? So why we are doing a regression is just to check whether first of all, you have to fit the model, and fitting just the model is not enough. There's a set of data. You can anyway fit a model doing certain things, but that model should be usable. That model should be useful. For that, the model should be significant, right? If the model is insignificant, although you have a model in hand, you're not going to add some value for it. You're not going to make use of it. So always when we apply the formulas for beta naught, beta 1 and all that, when we are after a model, we always have to check the model validity or the applicability. In that case, you have to perform a hypothesis test. How do you construct the test statistic if you do not know the distribution? Right? So that is why we are learning all this. At the end of the lecture, you will feel that these are too informative. You will feel like how you're going to get these to head. But I'm going to give you a summary, although I teach you here and there all these facts, because all these should be taught. But at the end of today's lecture, you're really going to use it. Then you will realize, oh, okay, this is why I learned this. So don't panic. This is not hard. You have to know the distribution of this in order to determine the pivotal quantity if you're constructing a confidence interval, or to determine the test statistic value if you are doing a hypothesis test. So that is the need of learning this. If you have questions, just interrupt me and ask, right? I'm just going through this one after the other. So yeah, sampling distribution of beta 1 hat for normal error regression model follows a normal distribution with mean beta 1. Why? Because this is an unbiased estimator. If you take the expected value of this estimator, it is going to be equal to beta 1. So mean is always the expected value. So that is why you put beta 1 here. It's easy to remember, right? You don't have to by heart this. If you know this is an unbiased estimator, you simply can write this. What you have to remember is it is normally distributed. With variance, this, of course, you have to know that. This implies that this particular quantity is standard normally distributed. If you know X is normally distributed with mean, mu, and variance sigma squared, what is our Z? Z is going to be X minus mu divided by sigma squared, right? Sigma squared divided by sigma. That is how you standardize a variable. That means from some normal distribution, you are mapping that to the standard normal distribution. So same thing done here. This is our random variable minus the mean. It's like X minus mu divided by square root of this. So that is basically this. You have standardized it, nothing rocket science here. You have learned all these, right? So if you have forgotten, learn it now. This is just a standardization of variable. The thing is, you can't see X here, you can't see mu here, you can't see solely sigma squared here, you can see some other variables. The thing is, you have to get this pattern to your eye. You have to train your eye in a way that you can identify these. So always, that is why it is encouraged not to by heart things like if X is n mu sigma squared, Z is going to be n01. If you train your eye in that way, you're never going to realize this. You always have to study it like this. If a random variable is normally distributed with some mean and some variance, to standardize it, you have to subtract the mean and divide it by the corresponding standard deviation. That is all you have to study. Don't study in terms of symbols and letters and all that. Then you're in trouble. So you don't have to put any extra effort to learn this. I'll repeat it once again. If a random variable is normally distributed with some mean and some variance, and if we want to convert it, map it to a standard normal distribution, that is 0,1, 0 mean and variance 1, we have to subtract the mean from the random variable and divide the quantity by the standard deviation, not the variance, but the standard deviation, so square root of this. Take it like that. You have to learn these notations just for the sake of answering the paper, because I'm going to use these notations. So this is basically variance. VAR is the variance of the estimator. So this one I'm going to have in notation, maybe not in the paper, but throughout the entire slide set, I'm going to continue this notation. So get used to this. Variance, if you want to compute the variance of this estimator, this is an estimate, it's not a parameter. You have a hat here, right? It's a function of observable random variables, I should say. Beta 1 is written in terms of x and y. So this is not a parameter. Seemingly it is a Greek letter, but not a parameter. There's a hat. Remember that. So variance of an estimator, you denote it like sigma squared this. If you want to get the standard deviation of this, then it is going to be the square root of this. That is why sigma squared this. This is a notation. If you want to get the estimated value of this variance, so this is the true variance. If you want to estimate this entire thing, that is VAR beta 1 hat, entire thing you put a hat. That is the meaning. If you are going to estimate this thing, so this is the variance of the estimated value. If we are going to estimate this particular variance, then you are using this notation, right? Because this is a parameter. You don't know parameters, population parameters. You have to estimate this somehow. So how you are going to do that? By using, this is not substituting s squared here. This is a notation. This is not multiplication, right? This is just a notation. If whenever I ask you to write the estimated value of the variance of beta 1 hat, this is the notation I'm using. This is just a notation. Estimated value of the standard deviation of this is simply the square root of this. So you don't have to study all these things. It's enough studying the first statement and the third statement, because second and fourth are basically the square root of the first and the third respectively. So it's not studying, just get used to this notation. Note that estimator of sigma squared is sigma squared hat, which is equal to the MSE, mean squared error. You take the errors, you square it, and you take the summation divided by the corresponding degrees of freedom, let's say, right? So you have averaged it out, right? You have averaged it out, the gap, the squared gap. Basically, this is the mean squared error. So it is given by sums of squares of errors divided by n-2. When we go to ANOVA table, you will get familiar with these things. For now, just skip that. If you are asked to compute the MSE, right, this is the formula. You have to know that. Take the gaps between the actual value and the estimated value, square them, take the summation, divide it by number of observation minus 2. That is the MSE. So you are going to make use of that MSE in order to compute this quantity. If you are going to estimate the variance of beta 1 hat, you have to make use of MSE and SXX. You have to calculate this, you have to calculate this, take the ratio. That is going to be your this one. This is going to be very useful when you are computing confidence interval. We'll do an example today. This is just notation, just scan this. You can try these proofs out. I think I did this one maybe in the first or second lecture. So you can try these ones. I'm not going to test them. Okay, sampling distribution of beta 1 hat where sigma squared is unknown. If that is the case, you see This is the pivotal quantity, right? Earlier, what did we have? This one, right? This is normally distributed. So here, what do we have? Beta 1 hat minus beta 1 divided by this quantity. If we take this quantity as the pivotal quantity, it says it is T distributed with n minus 2 degrees of freedom. Earlier, what did we have? We had beta 1 hat minus beta 1 divided by some other quantity, which is standard normally distributed. Here, what do we have? Beta 1 hat minus beta 1 divided by this. That is what? This one. So this is, here we had MSE, mean squared error, right? That is the only difference. Here we had sigma. If we know the population parameter, you can assume this to be standard normally distributed because we can plug in the value here. But what if we don't know the population variance? You can't put capital S here, right? If you don't know the population variance, you can't simply easily plug in the sample variance to the population variance. That is wrong. That is why we have to estimate it. So on behalf of this particular thing, if we substitute MSE, the distribution is going to be changed. If you know sigma, yes, you can put this. But in case if you don't know sigma, you make use of the sample variance in order to compute this pivotal quantity by the use of MSE, then it is T distributed with n minus 2 degrees of freedom. So this is highly used. Right. So sampling distribution of beta naught, it's equally important to know the sampling distribution of beta naught as well, in case if you want to construct a confidence interval. But we usually do not perform hypothesis tests for beta naught because that is the beta naught is the intercept term. So whether beta naught is there or not, model existence really depends on beta 1 because that is the one which is connected with X. If we take a model, if we take this model, what if beta 1 is 0? Just assume beta 1 is 0. This whole term is cancelled out, right? So yi is equal to beta naught. So this is not a model. Yi is a beta naught means you have a straight horizontal line. You have to change y depending on x. So this term should be non-zero, or you call it in statistical term. In mathematics, you said this should be non-zero, but in statistics, we don't give exact values. What we say is this term should be significant. Even this is 0.0001, it is mathematically existing, but the relationship is very weak, right? In that case, it's very weak. This the value of xi is reduced, right? The weight of this is very less if this is very close to 0. In statistics, we check whether this parameter is significant enough. Of course, it has to be non-zero. If it is 0, we are definitely not making use of this model. But if this is even very close to 0, sometimes we might get a conclusion from hypothesis testing that this term is not significant enough, which implies it is something like this is equal to 0, right? So for that is why we perform hypothesis testing and constructing confidence intervals and so on for this. Even we can construct confidence interval for this, but we are practically not doing hypothesis test for this because it's not needed. This is the most important part of it. To have this model, to include x here in this model, because y is varying because of x. If this doesn't have a significant relationship, this is going to be insignificant. You can't let x be 0. X is the observations that we have, right? So what you can let is this one be 0 if you want to make the model insignificant. So our intention is to come up with a significant model. That is why we do all these. Right. So just for the sake of constructing confidence intervals, it's important to know the sampling distribution of the intercept term as well. So beta naught hat is this. This is the least square estimates of beta naught hat, right? This is a linear combination of yi. Hence, the sampling distribution of this for a normal error regression model always follow a normal distribution with mean beta naught and variance this. So what is the distribution of beta naught? Normal with mean beta naught. Of course, y expected value of beta naught hat is what? Beta naught. So normal beta naught, variance is this. They say the variance of beta naught is this. This is by the notation. This is how you write. Beta naught hat is distributed normally with mean beta naught and variance this quantity. So it's important for you to learn this as well. This might not be given in the exam. The formula might not be given in the exam. So you have to know this. The variance of beta naught hat is this. Or else you have to prove and get it. Good if you can. Otherwise, you have to by heart. The proof is not tested in the exam. But what you have to do is variance of beta naught hat. So we have to take the variance of this quantity and simplify up to here. Try to do that as a homework, right? Otherwise, you have to by heart this. Right. Yeah. So as an example, I have given, I think this one I proved last time. Not properly, but I showed you. It was not a proper proof. I showed you how that is happening. This one, just try to get it. This is basically the variance of this. Estimated variance is something else. This is the variance of beta naught hat, right? I told you that I'm going to use this notation throughout the lecture slides. This is variance of beta naught hat. So try to come up with this. The starting point is variance of beta. You take the variance both the sides of this. You know how to do that. So try to get this later on, not now. So anyway, I won't give questions like this at the exam. Right. So I know that this is too informative. When your sigma squared is unknown, right, you have to come up with some alternative, right? So this pivotal quantity, so you know, if this particular thing is normally distributed, if this is happening, right, you know, you can standardize this. How? You subtract the mean, that is this, by this and divide it by square root of this, which will give you standard normality. That is how you basically standardize a random variable, normally distributed random variable. Okay. So yeah. So it is done like that. But in case if you don't know sigma squared, what's going to happen? You have to have some alternative. So that is this, making use of MSE once again. Whenever you plugged in MSE or whenever you estimate the unknown variance parameter, it is going to be distributed as T. In earlier case also the same thing. When we are getting the pivotal quantity of beta 1, when we standardized it, it was standard normally distributed if we know sigma squared. If we don't know sigma squared, that quantity was distributed as Tn minus 2. Just because we had to estimate the variance, because we don't know the variance. In case if we know the variance in beta naught hat, simply it follows a normal distribution. Even you can standardize this, doesn't matter, right? In case if we don't know sigma squared, you have to estimate sigma squared. Whenever you plugged in the estimated value to the pivotal quantity where sigma is placed, the distribution changes to T. That is all what I want to summarize to you. So this particular quantity, when you subtract the mean and divide it by the estimated variance of beta naught hat, it is going to be distributed as T with n minus 2 degrees of freedom. Right? Here, this quantity means basically this one. It's easy. Here on behalf of sigma squared, you have put MSE. Nothing to complicate here, right? Instead of sigma squared, you have put MSE, right? Because we don't know, if we don't know the value of sigma squared, how can we substitute here? It's not known. So we have to estimate it by MSE. Whenever we put MSE here, the distribution changes. That is all what I want to say. Earlier, if we had sigma squared, it is normally distributed. If we have MSE, it is T distributed. So don't confuse things out. This is a very small thing, right? You have to read this carefully when sigma squared is known, when sigma squared is unknown. What are the sampling distributions of beta naught and beta 1, beta naught hat and beta 1 hat? Okay, estimates. You can make a short note, right? Sampling distribution of beta naught, sampling distribution of beta 1. If you fill this table, it's easy, right? Sampling distribution of beta naught hat and beta 1 hat when sigma squared is known, when sigma squared is unknown. This is basically the short note you have to make, right? When sigma squared is known, you have a normal distributed with beta naught, and I can't remember the formula. Put the variance here. This is normally distributed with mean beta 1 and something, right? So you have to write the quantity as well. Right? Here, beta naught hat minus beta naught. I should say beta I here. I can be 0, 1. Beta I hat minus beta I divided by S beta I hat, because I for beta naught and beta 1, right? So if this is the quantity, this is T distributed with n minus 1 degrees, n minus 2 degrees of freedom. So just put the values here, I can't remember. But you have to remember, right? So sampling distribution of this, sampling distribution. So this is what we discussed so far. When this is known, when this is unknown. So when you're given a question to construct a confidence interval or whatever it is, to do any computation, it is important for you all to know whether this is known or this is unknown in order to specify the distribution of it, whether it is normal or T. That is the idea. Okay, logic of inference. So this is given for you just to make you eye opened, right? You have a population, right? Population has some parameter, right? Out of the population, we take a sample and we have data. This data doesn't have everything in the population but a sample out of the population, some proportion of this population. And we use some statistic to make inferences about the population parameter. Just because we cannot come directly from here to here, we have to go along this cycle. We take a sample and we have data. We construct some statistic where we know the distribution. Then we can make inferences about the population parameter. Basically, by using data, by constructing a suitable statistic in order to determine the population parameter, we are going to estimate it. If we want to estimate the population mean, we are taking sample mean as our statistic to make inferences. It can be a point estimator, it can be a confidence interval, even it can be a statistical hypothesis test. Whatever the technique it is, you have to go in this order to make inferences about the population parameters, either it is mean, variance, median, mode, anything. So this is the logic why we are using inference. Confidence interval for B1. See here, we are going to make use of these MSCs and all that. Since this quantity follows a Tn minus 2 distribution, we can make the following probability statement. So this is the starting point where you are asked to construct a confidence interval for 1 minus alpha 100%, right? If you want to have a 95% confidence interval, what is alpha? 5%, right? 1 minus 5%. So that will give you 95%. Here you write the probability statement. This is the pivotal quantity of interest. Just because we know this is T distributed, this is the lower limit, this is the upper limit. It's very easy, right? We have the pivotal quantity here. I'll just write that to you. If you have forgotten. So this is a T distribution, just like the standard normal distribution. It is symmetric around 0, but it is not standard normal, it's T distribution. Okay, symmetric around 0, right? So you take the upper tail value, you take the lower tail value. This is alpha over 2, this is alpha over 2. The probability is given by the area under the curve, right? So you denote this quantity, quantile, by T alpha over 2. Let's say degrees of freedom is equal to n minus 2. So you can write something like this. You can even interchange Tn minus 2 alpha over 2, right? You write this quantile as T 1 minus alpha over 2. Okay, why 1 minus? We always read from this side. This is alpha over 2. You know, the total area under the curve is 1. So if it is 1 minus alpha over 2, you are getting this quantile. You read from this side. Okay, just because this is symmetric, you can say this quantity is equal to negative value of this. It's something like this. If you take the number line, right? This is -1, right? Keeping the same gap here. If this is 10, this is -10, keeping the same gap here, just like that. You have a same gap from here to here and here to here, right? So this quantile is, by notation, we say it is 1 minus alpha over 2, right? Still, you can write it in terms of this, just because of the symmetry that it has. So when you are constructing a confidence interval, you can say probability that the particular quantity falls in this white region is between this and this one, right? So you have to write this quantile and this quantile. That is what I have done here. This one and this one. So it is interchanged, right? This should come this side. Okay. Can you please change these two inequalities? In some books, they denote it the other way around, right? If somebody says this quantile is T alpha over 2, they say this quantile is T 1 minus alpha over 2. In some books, they read from this side. But anyway, if this is this one, this quantity should be this one. I mean the notation, right? Values are the same. If you denote this term in this way, this should be this one, right? If this is negative, if this is 2, this is negative 2. Notation really doesn't matter, right? But the general way is writing it from the from this side itself. So yeah, it's okay. Just leave it like this. It's okay. As long as you know this quantity is lying between these two limits. Notation really doesn't matter. And you can put this one here and this one here, doesn't matter. Just because these things, the absolute value of these things are equal, right? Just because that happens, you can write the confidence interval as beta 1 hat plus or minus. This plus or minus comes because this particular thing is equal to negative of this. That is how this plus or minus is coming, right? So you put this quantity here and this one. So what you have to is, you have to cross multiply and isolate beta 1 hat in the middle, right? That is how you usually do. Rearranging the above, you have to rearrange it, right? Rearranging the above inequality, you're getting something like this. Statistics is never having to say we are certain. Of course, how do you interpret a confidence interval? That is very important. You cannot say probability that the beta 1 is lying between the lower limit and the upper limit is 95%. You can't say like that, right? When you take a sample out of the population, if you get a good sample, of course you have the particular parameter in the constructed confidence interval itself. Otherwise, it is out. 95% confidence means that is not really the probability, right? So if you look at this, all these red lines, they are out of bounds. This is the population parameter value. These are the confidence intervals constructed for this. So all these confidence intervals contains, all these blue confidence intervals contains the parameter. These red ones do not contain the parameter. What do you mean by 95% confidence? Let's say you draw 100 samples out of the same population and do the same experiment 100 times. So when you have 100 samples, you have 100 confidence intervals, right? 95% confidence means out of the 100 confidence intervals that you constructed, 5 of them are out. Only 95 of them contain the true parameter. That is what it says. What is the probability that the parameter is between the two values of the confidence interval? It is either 1 or 0. How do you say that? If it is a good sample, if the confidence interval really contains beta 1, so the probability that the beta 1 lies between the two values is 1. 100%, that is 100%. In case if beta 1 is not lying between the two values of the confidence interval, in case if beta 1 is not included in that particular range, the probability of beta 1 being in that range is 0, because it's not in that region, right? It's 0%, 0 probability. So probability of a parameter to be within the confidence interval is either 1 or 0. At times it is 1, at times it is 0. So how do you interpret a confidence interval? We are 95% confident that the parameter lies between the two values that we constructed, right? So probability and confidence are two different things. Although it seems to be the same, it is not the same. Again, probability that a parameter is lying between two values is either 1 or 0. If the parameter is there, it's 1. If the parameter is not there, it's 0. Right? The confidence that you have on your constructed interval where the parameter has some inclusion in that particular interval is 95%, 0.95. Okay, so don't confuse out when you're interpreting. Please be specific. Don't misinterpret. That is a place where even great statisticians go wrong. So don't go wrong in that. Right. Okay, so as an exercise, we'll do this. Yes, we have time. I'm thinking whether we are doing it now. I'm going to discuss this. Let me finish off all the teaching parts, and then it's easy. At the end also, we have a small part to do. I'll revisit this example. So you have to make use of air freight breakage example in the previous lecture note. I have the data set. I'll give that to you. So we are going to discuss this today. Just keep it for the moment. Confidence interval versus significance test. Okay. The two most common types of statistical inference are confidence interval and significance test. Basically, confidence interval technique and hypothesis testing technique. That is what it says. We use confidence intervals to estimate a population parameter, and we use significance tests to assess the evidence in the data for some claim about the population. In hypothesis testing, we don't really make inferences about the population parameter. We check it with some value. For example, under H0, we put population mean is equal to some value versus population mean is not equal to some value. We are checking a condition. Or we can have directional hypotheses. Population mean is less than or equal to some value versus population mean is greater than some value. Things like that. So we are checking statements, we are checking hypotheses. That is a test, right? Confidence interval can give you some idea about the range where the parameter can fall, but with some percentage. It's not 100% confidence, right? Okay, so the vocabulary of significance test, the statement that we are trying to find evidence against is called the null hypothesis. We usually denote it as H0. This is how it's pronounced. So you all know this, which means null. Null means no effect. H0, not means null. N-U-L-L, null, right? No effect, no difference, no relationship, no association, nothing. All those statements comes under H0. If mean is equal to 5, that means it's equal. There's no difference. Equal means no difference. That is why we put always the equality sign to H0, which gives out the meaning null. Right? That is how you determine whether we are going to put this particular phrase to H0 or H1. You all have worked with these. Statement that we are trying to find evidence is called the alternative hypothesis. Or the complete opposite of that. We denote it as HA or even H1. You can put, so as this is alternative, some people say it's HA, you can put H1 either, doesn't matter. Important, hypothesis always refer to a population. So this is where people go wrong, I don't know, without knowing or with knowing, it's very wrong. Hypotheses are always refer to population. We are not interested in checking a sample statistic because we have the data set. We know how to compute mean, median, variance, mode, and all that. All the summary statistics we know how to compute out of the data. What we are interested is about the population. So why we are doing a hypothesis test is to estimate the population parameter, not the sample statistic, right? We should always state H0 and H1 in terms of population parameters in that case, right? Expressions like these does not make sense, right? Beta 1 hat t is equal to 0. No. Beta 1 equals to 0. So this is a H0. If you are checking whether beta 1 is equal to 0 or not equal to 0, your null is beta 1 equals to 0. If you write beta 1 hat is equal to 0, it doesn't make any sense because you are referring to the estimated value. We are not doing hypothesis test for estimations. We are doing it to determine the population parameter. So don't write things like this. It's going to be completely wrong. The probability computed assuming H0 is true, that the outcome would take a value as extreme as that observed is called the p-value of the test. So you might have done hypothesis testing by using p-value, by using critical values. So I'll recall that, right? If you have some distribution, let's say this is your critical value or table value. I don't know how you learned that critical value. The value that you keep either to reject H0 or accept H0. So let's say you are considering the upper tail as the rejection region. Okay, this is the rejection region. Whenever your test statistic value falls in this region, somewhere here, you are going to reject the null hypothesis, right? What do you mean by the p-value? You are computing a test statistic, right? So it can fall either here or here, right? Let's say it's falling somewhere here where it's not is accepted, not rejected. So let's say this is our calculated value of our test statistic, right? P-value is basically area under that curve. This is p-value. It's again a probability. This red part is what? Significant value, alpha. Alpha is a significance level. It's also a probability. That is why we make the decision rule all the time with regards of p-value. Reject H0 if p-value is less than alpha. That is why we form our decision rule of rejection like this. If p-value is less than alpha means what? The area shrinks up to somewhere here. So the p-value, the probability value is less than our significance value, which means it falls in the rejection region, even it in the other case. Let's say this is our rejection region, right? Let's say your calculated value is somewhere here. So this is going to be the p-value. Still, even if it is in the other end, if p-value is less than alpha, alpha is this entire region, p is this entire region. If p is less than alpha, you're going to reject H0, right? So that is what they say. P-value measures to what extent the data is consistent with the null hypothesis. The smaller the p-value, the more evidence against H0. Against H0. Against H0 means we are tend to reject H0. Against, going against something means what? You don't like it. You try to reject it. One versus two-sided alternatives. So it is not always easy to decide whether alternative should be one-sided or two-sided. An alternative should express the hopes or suspicious we bring to the data, but should be formulated before we collect the data. If you do not have a specific direction firmly in mind in advance, you can use two-sided. I think it is there. Something like this, they're saying. So we are checking whether beta 1 is equal to some value, but we don't know whether we form the alternative as beta 1 not equal to or greater than or less than. If we don't know this, it's better to go for two-sided case. That is what they say, right? We don't have alternatives for H0, but we have alternatives for H1. That is why it's called alternative hypothesis. You can have alternatives. So you have to decide on that. prior to the experiment. We sometimes take one final step to assess the evidence against H0. We compute the p-value with a fixed value that we regard as decisive. The fixed value is called the significance level. I just told you what, right? Because we are checking it with some significance level. Typical values of alpha 0.05 and 0.01. You can use any value. Doesn't matter, 5%, 1%, even 10% doesn't matter. Usually we use these two. If the p-value is small or smaller than alpha, we say that data are statistically significant and alpha, which means simply we reject H0. So we reject H0 means there's no null. We reject this means one of these, which means beta 1 is significant. Let's let beta 10 be 0. This is some hypothesized value. Okay, basically what we check is whether beta 1 is equal to 0 or not. You can put any value here, but to check the model significance, what we do is we let beta 1 equal to 0 or beta 1 not equal to 0, right? We reject H0 means what? Beta 1 is not 0. That means the model is significant. In case if we had to accept H0, that means our slope parameter is 0. That means there's no model, right? There's no significance in the model. X and Y are not related in that case. The relationship is very weak and as weak as 0, right? That is what it says. Okay, so if we have smaller p-values, we intend to have smaller p-values in order to reject H0 to make our model significant, but we have to check that. Tests concerning beta 1. According to the sampling distribution of beta 1 hat, we can obtain the test statistic to test claims about beta 1. So basically, we know the sampling distribution of this quantity, which we discussed before. It is T distributed with n-2 degrees of freedom. We make use of this quantity to test the particular hypothesis whether beta 1 is equal to 0 or not, right? So this is the test statistic of interest. Our H0 is beta 1 equal to 0 versus beta 1 not equal to 0. So basically use this one and this one, put 0 here. You don't have to go for alternatives. So this is given for whenever you do research, if you really want to specify something, if you want to know something specifically, you go for one of these if you want to check. Otherwise, if you have some prior idea about the parameter value, otherwise simply you go beta 1 equals to 0 versus beta 1 not equals to 0. This is the test statistic value, basically the pivotal quantity of interest, which is distributed as Tn-2. So whenever we calculate this, this is going to be our critical value. So we can form the hypothesis and see how it goes. Revisit air pressure. Okay, so we have around 1 hour time. We can slowly go through this. So at the end, they're asking us to revisit air freight breakage example and test whether there is a linear relationship between the number of ampoules broken and number of times the cartons is transferred from one aircraft to another. Right? This is the one that we discussed last time. They are talking about this one, this example. We built a model for that. Y equals 10.2 plus 4 times x. That was our model. We determined the values of beta 1 and beta 0. Now they are asking whether the model is significant. What do you have to check? You have to check whether the value of beta 1, yes, it is 4, right? But that is based upon the formulas, right? We have to check, hypothetically check whether that is exactly happening. It really depends on data. It depends on the sample. If we take another sample instead of this, you're getting some other values of beta and beta 1. Maybe very close to whatever the values that we got, 10.2 and 4, right? But you definitely should be getting some other different values, which may be very close, right? If this is a good sample, well, it should be close enough, but different. So we have to check whether actually this beta 1 is 0 or not, whether beta 1 exists or not, to see whether this particular thing is the model built for this particular data set is significant enough, right? So before going to that, we'll go back to the skipped example. We are going to work that out. So ready your pens and papers. We are going to do this, right? I will help you with this. So they are asking you to revisit the air freight breakage example and compute the standard errors of basically the standard deviations of the estimates of regression coefficient. So they're asking you to compute this one and this one at the first place. So this is the data set. This is the data set, and we computed this particular table. So make use of that as well, right? So x-axis is there, x bar is there, right? So you have to compute a very little couple of things. So I'll help you in that. In order to compute this one, right? I'll help you because I have to share you two screens. Many of you might have not taken printouts of the lecture note. I know it's really hard to slide through things and also look at the lecture, so I'll help you with that. So this is our model. We constructed this model that day. This is our model. We are going to check whether, first of all, we are going to get the estimated standard deviation. So there's no square here. So estimated standard deviation of beta 1 and beta naught. Right? I'll give you the formulas for this. It is there in the slides. Just because it's hard to scroll, I'll give you the formula. So this is just a practice session sort of. Okay. This is if the sigma squared is known, you can put sigma here, right? But it is unknown in our case. All what we have is data in hand. These are the formulas. So think of a way of computing this quantity. You haven't computed MSE as well, right? So you have to compute that as well. I'll guide you to do that. Why? Because MSE is equal to what? This is MSE. So you have to get this quantity, right? And in air freight example, right, our sample size is 10. So you simply can get this. Our MSE would be summation I goes from 1 to 10 yi minus yi hat squared. I'll give you time for this. Just look at the board. This is 10 minus 2. So you are supposed to compute this quantity in order to compute MSE. You have to compute MSC in order to compute this quantity. SXX is already computed in that table, so you can use that value without wasting time. So how are you going to compute this quantity? What does this really mean? The gap between the observation and the fitted value, right? So for that, in order to compute this quantity, I would guide you. Just write yi's here. 16, 9, 17, likewise up to 11. Okay. And you have xi's here. That is 1, 0, 2, likewise up to 0. I'm writing the data set. Okay. Then have a column for yi hat. How do you get yi hat? By using this formula. You know the value of xi here. You substitute 1 here. Take y1 hat, this quantity. You substitute 0 here. Y2 hat is equal to some quantity. Then you substitute 2 here. Right? You have to substitute these x values in the model and compute the yi hat column. You know yi column, you know yi hat column. Now you have to get yi minus yi hat, right? Then you take yi minus yi hat whole thing squared, right? Just have these columns written. I'll give you time. We have enough time to work this out, right? And when you have this quantity, it's just the matter of taking the summation here. That will be plugged in here, right? So this quantity is going to be the summation of all these, this one, okay? Then you know how to compute the MSE, plug that value in here. SXX is already computed. So take this quantity. Now try it yourself. I'll just take a screenshot of this. No, what you have to do is just compute this just write these columns in your paper. yi, xi, yi hat, this one and this one. I'm just guiding you to do this, okay? This is how you should think. You have to fill all the 10 columns, 10 rows here, right? I will show you the data set in the screen. Whenever you are done with computing this, put the answer in the chat room. Don't go to this. We'll discuss this one next. So if you know the MS is just the matter of plugging in. If you can compute this. Also, first compute this quantity. I'll show you the data set. If there's any question, please ask. This is the data set. yi, xi. Instead of all these, have those columns. Yi hat, yi minus yi hat, and this column. So fill those columns, you will get the answer. So this is the data set. I'll give you this one. Yi's are there, xi's are there. Now try to do it. If you have questions, please ask in the chat room. Yeah, now do it. And whenever you finish, put the answers in the chat room. I'm waiting till you respond. I hope you all have copied these 2 lines. Just as columns, it's easy if it is column wise. So now I'll share the whiteboard so that you can refer to the formulas there rather than scrolling the slides. So let me share the whiteboard. Take time and do. You have to do this one. Okay, someone has answered in the chat room saying that he or she has got a value for that. Let's see. Yes, your answer is correct. Okay, another person, I'll just call out by the index numbers. Is 2018-341, your answer is correct. Is 2018-343, your answer is correct. I think y'all are getting the things now. Thank you very much for responding. And others also, please try. And the ones who responded, you all can try the next one. Get the value for S beta naught hat. So those who have not done, don't panic. It's okay. Slowly get it done. Others don't waste time. Okay, is 2018-306 also has responded correctly. Right. So I'll work that out on the board so that you all can those who find it difficult, just because this is the very first time, those who find it difficult can really get some idea. How should I do that? Others, please try the rest of the questions. In case if you find it difficult, in case if you didn't understand what to do, please ask me now, because these kind of questions you will be getting for the exam. So I won't repeat yi and xi columns because they are there. So I'll repeat yi hat column, which means you have to plug in all the x values in this formula and obtain yi hat. So in order, I'll write that column. This is 14.2. Check your answers. 10.2, 18.2, again 10.2, 22.2, 14.2, 10.2, 14.2, 18.2, and finally 10.2. Then I got yi minus yi hat. So this is 1.8, negative 1.2. That is repeated. 1.8, negative 0.2. Sorry about the alignment. It's hard to write straight away. 2.2, 0.8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Then you have to take the square of it. Right. So this is 3.24, 1.44, 1.44 once again, 3.24, 0.04, 1.44, 4.84, 0.64, 3 times. Right. So how are you going to get the summation of this? Just add all these. So you would get 17.6, right? So your MSE would be summation of this, that is 17.6 divided by n minus 2, number of observations minus 2. Here we have 10 number of observations, we have 10 observations here, 10 rows. So it is going to be 8, MSE is going to be 2.2. Right? While you were doing this, I made use of my favorite software in R, and you don't have to know this, right? I just had these things included, and I modeled, and I fitted the regression line, and just typed ANOVA. So in this table, I got, so mean squared errors is the residuals actually. So residual mean squares of residuals is the same as mean squared errors. So I got it as 2.2, which I cross-checked. My answer was correct. Right. So this is easy. But you can't do this at the exam. You have to go for manual calculations. So get used to this. But whenever you want to cross-check, you can try things like that. So when you know MSE, it's just a matter of substituting it here. So this is basically, don't forget the square root, because they're not asking you the variance, they're asking you the estimated standard deviation. So this divided by SXX we computed last time. So SXX is 10. You should get 0.469. The ones who responded this are correct. For beta 0 hat, S beta 0 hat 1 is 2018 343. You have answered correctly. There were some other people who I didn't speak out the index number also have answered correctly for the first part. There's one person who had not answered correctly. I'll just tell the answer. He or she has put 0.1483. So please check your answer once again. 0.1483, nothing like that is coming. So answer should be this. So just try that. Make sure you do your calculations carefully. Most of you all have gotten this answer, which is correct. So for this one, it's just a matter of substituting. So you know MSE. Should I erase this and write it properly? MSE is what you found out to be 2.2, right? So 1 over number of observations plus X bar was found out previously, that is 1. So how do you find out X bar? Add all these, including zeros, divide by 10, right? If you including zeros in the 10 sense, you have to divide it by 10. You can't forget about these zeros and add all these and divide it by 1, 2, 3, 4, 5, 6. You can't divide this by 6. Okay, remember that. When you're computing X bar, you have to include the zero. The zero is also an observation. So there you go. You have 1 squared there. Sx is 10. So there you have this is 2 over 10, 1 over 5 times 2.2 square root. That is something like this. So there's some other person who had answered correctly. Is 2018 474. Yes, your answer is correct. Good. These are not hard things. My intention was to let you compute this without making any errors. Because if you make an error here, when you construct the confidence interval, it's going to be problematic. Because you're making use of this quantity in order to construct the confidence interval. So whenever you get some wrong figure here, entire set is going to be 0. It's going to be wrong, so I cannot mark it right depending on whatever the value you got here. So be careful in regression paper. When you make something wrong initially, that continues till the end. So carefully go for your calculations. Right. So those who have tried these two can try to come up with the confidence intervals. I'll show that to you. This is the question. Obtain 100 alpha 100%, 1 minus alpha 100% confidence interval for beta 1. So you have to check what is the formula for beta 1, where sigma squared is unknown. So you have to make use of the computed value, this one, right? So you know that pivotal quantity beta 1 minus beta 1 had divided by this is going to be what? T distributed. So you have to make use of that as well. So try to obtain a confidence interval here. I'll show you the formula for that. Confidence interval for beta 1 is basically this one. So you know this quantity. You know this quantity. You have to find this out. right? Actually, so just write this down first. 1 minus alpha 100% confidence interval for beta 1 is given by this. Write this down first. I can't share a couple of slides together, that's fine. Write this down. Okay, this is computed, this one you know, which is 4, right? The model parameter, estimated model parameter. To compute this one, make use of this table. I think this part is enough. You don't need the entire table. So I gave you a hint. This part is enough. By using this table, construct that particular confidence interval, and in the chat room, give me the lower limit and the upper limit. So basically, let's say it is this beta 1 is lying between 10 and 50. For example, I just gave random numbers. Okay. So in the chat room, please write a bracket 10, comma 15 and the closing bracket. So I want some answer like that. Try. I got 2 answers. One answer, I think you have to check once again. The other answer is correct. I'll call out the index number where the answer is correct. AS 2018 341. Your answer is correct. So there's only 2 people who responded. So the other person has to check his or her answer. There's a slight gap. Just see where you have missed. We need the confidence interval for beta 1, okay, not beta naught. So just check that once again. I doubt it whether you went wrong with reading the table value. So if that is the case, I have to teach you. Right, okay, others don't respond. Why is it so hard? Okay, let me do that for you. I will clear these things off. What I want is to construct a confidence interval, which is 1 minus alpha 100% confidence interval for beta 1. So let's take alpha equals 5%. Okay, you have to know that. So if alpha is 5%, this is going to be 95% confidence interval. Right. So what is the term beta 1 hat plus or minus t n minus 2 comma alpha over 2 times s beta 1 hat. Check whether you wrote this statement properly. For 1 minus alpha 100%, this is the statement. Then for 95% confidence interval for beta 1, make sure you don't write hat here because we are constructing the confidence interval for the parameter, right? By making use of the estimated value. So don't confuse things out. Don't write hats here. That is meaningless. We don't construct confidence intervals for sample estimates. That is meaningless, right? We don't have to. So properly write that. So what is the value of beta 1 hat? This is our model. Yi is equal to 10.2 plus 4 times xi. So this is basically beta naught hat. This is basically beta 1 hat. So what is the value of beta 1 hat there? That is 4. Plus or minus, what is the t value? T, n is what? In our air freight example, n is 10. right? So we have to take 8 degrees of freedom. Check whether you wrote this properly. And alpha is 0.05, which is 5%. So alpha over 2 is 0.025. 0.05 divided by 2 times, and we previously computed this quantity, which is 0.469. You have to read this value from the table and see whether you read that properly. How do you read that? T8 0.025. Yes, another person had answered correctly, but have interchanged the lower limit and the upper limit. As 2018 481, your numbers are correct, but when you're giving a confidence interval, always give the lower limit in the left hand side and the upper limit in the right hand side. Okay, what I say is you can't write intervals like 5,2. How do you write it is 2,5. So whenever you write it like this, it is marked as wrong. So I know things like that happen when you compute this plus first, and when you compute this minus first, things like these happen. I know it's a careless mistake. And that frequently happens in general case. I emphasize that in order to make you aware things like that happen, and be careful with those things, right? But good attempt in computing the values properly. So let me show you the table and how to read T8 0.025 from the table itself. So degrees of freedom is 8. So you have to go along this line, this row, right? The tail probability is alpha over 2, which is 0.025. So that is this one. Don't confuse, it's not 0.25, it is 0.025, right? So you have to go along this row, this column. So this column and 8th row, it is basically this part, this value. See whether you got this 0.025 and degrees of freedom 8, the value is 2.306. You have to properly read that from the table. If you didn't read this properly, it's again going to affect your final interval, right? So when you compare this, you should get, you can either put a curly bracket or this bracket. What do you mean by this bracket? Including the value, right? What do you mean by open bracket? Excluding the value. But when it comes to confidence interval, you can either include or exclude, that doesn't matter. That is why I put a curly bracket, but you can choose whether you are going to put this one, or the curly bracket. Curly bracket means, in my notation, curly bracket means it can be either this or this, right? So you can put any bracket that you like. So I'll put the square bracket for the moment. So it is going to be 4 minus 2.306 times 0.469, comma 4 plus this quantity 69. So you don't have to expand and write these things after this point. You can simply put the value. Okay. What I showed you was you have to have the minus term to the left and plus term to the right. So the final answer is 2.9185, 5.0815. Having 2-3 decimal places is enough. You don't have to have a lot of decimal places, but make it correct. Like if you're having 2.91 here and stuff, so that is inaccurate. I won't mark wrong for that, but when you're rounding off, just follow the proper rules, right? I don't mark wrong for those things. But in case if there's a very high deviation, I can't give you full marks. So do a proper job. You can have 2 to 3 decimal places. It's okay. Round off properly. So this is the answer, 2.91 992 and 5.08. So interpretation, the most important point here. I'll write it, so please copy it and practice the way of writing the interpretation. We are 95% confident that beta 1, it's not beta 1 hat once again, okay, it's beta 1. Beta 1 lies between these two values. Okay, so let's say you have the confidence interval like this, but when you are interpreting, you don't want to have all these decimal places included. You can simply say this is acceptable, right? First, you have to show the confidence interval in real terms. You can simply say 95% confident that beta 1 is between 2, so you can say 3 and 5 approximately. So this word is a must if you are rounding it off to the nearest integer, right? But please round it off correctly. Don't write 2 and 5 because it's wrong, right? This is not 2. So I encourage you to use this way. But if you are rounding it off even further, just use this word approximately. Always have at least one decimal place that is, that is better. 2.9 and 5.1. Yeah, it's enough. So don't say the probability that beta 1 lies between these two values is 95%. That is wrong. Okay, don't use the word probability there. This is the statement. Okay, the next and the last question for today's lecture. This one. Revisit this example and test whether there is a linear relationship between these two with 5% level of significance. So that is a hypothesis test. I'll tell you what this really means, because we can simply do the calculations, but you have to get the idea behind this. So basically our model is what yi is equal to 10.2 plus 4 times xi. So they're asking you whether this model is significant or not, right? To let this model significant, what is the necessity? This term should exist, right? If this value becomes 0, this term does not exist. I know this value is visible to be 4, but that is for this particular sample. But if somebody else takes another sample, it could be close to 0, 0, whatever the value it is, right? So that is why we are checking. Okay, for this sample, this is the model, whether we can really apply this model to the population. We can apply this model only if this model is significant enough and it has a good predicting ability. We'll check that later on, right? So first of all, we have to check whenever we come up with a model, we have to check whether the model is significant, which means this xi exists, right? So for that, what should you check? Xi is xi. This is the thing depends on the sample. So this is basically beta 1 hat, right? So we are checking whether in real terms, population has beta 1, sample has beta 1 hat, right? So we are checking whether beta 1 exists in real terms. This is what we check. We are not checking whether beta 1 is 0 or not. because beta 1 hat is not 0, it's 4. For this sample, this is 4. For another sample, it could be 4.1. For another sample, it could be 3.9. For another sample, once again, it could be 4. For another sample, maybe it could be 1.4, something like that, which is totally different, right? So whatever the sample, it is changing, but majority of it should go align with this if this is a good sample, right? So seemingly this is a bad sample. What we are checking is not in the sample data we know, with this population beta 1, whether it exists, because we are making this model to the population, not to the sample, right? So we are checking this. What do we check? Under H0, we check whether beta 1, not hat, okay, that is meaningless. Beta 1 hat is 4. We are checking whether beta 1 is equal to 0 or it's different from 0. This is the hypothesis of interest. So for this question, I will write and show you the steps. I'll clear this off and write it properly. For this question, write you have to write all these steps. Okay, and you know the test statistic, you have to study that. So basically it is denoted by this. You can put any letter here, but that is of course the test statistic. This is the test statistic. So you have to study, you have to know this is the test statistic and the distribution of it, right? So you have to plug in the values. Beta 1 hat is what? 4. In our model, it's 4. This is the hypothesized value that we are checking. So that is basically this. And this quantity we computed 0.469. We computed in earlier case, right? So this is 8.5288. Just get the value. Next one is computing the critical value in order to test this, right? What is the critical value? This is Tn minus 2 distributed. So critical value is T 10 minus 2 alpha over 2, right? So this is basically T8. And we found this, we read this out from the table earlier. It's going to be the same value, 2.306. You have to read this from the table. Now form the decision rule, right? Decision rule. You have to write all these. Remember that. In case if you miss the decision rule or the decision or the conclusion, you're going to lose marks. You have to specify the decision rule. What is it? Reject H0 if the absolute value of T star, the test statistic value, is greater than T critical. Oh, how did you form this? You would be wondering, how did I know this? Why? It's easy. This is your T distribution, which is symmetric around 0. This is a non-directional hypothesis, right? What does it mean? This is your beta 1 axis. You have 0 here, right? What is our alternative? Beta 1 is not equal to 0. So beta 1 can take any value even below 0, even above 0. If H1 is correct, or in other words, if this is happening, H0 is rejected. What is H0? Beta 1 is this value. H1 is, beta 1 is any value different from this. So we reject H0 if this particular thing happens. Okay. So what is the rejection region? Rejection region means H0 rejection region is these two regions. From this one and this one, we decided, okay, these two regions. Our level of significance is alpha over 2. Alpha. So each side alpha over 2. Totally, it gives you out alpha. What is the value here? T alpha over 2. This you can either say T alpha over 1 minus alpha over 2, or you can simply say, just because of the symmetricity and it's around 0, you can say negative T alpha over 2, negative value of this, right? So actually the decision rule is reject H naught if your calculated test statistic value falls either here or here. It can be either the sides, right? But rather than checking two things, it's easy to check the absolute value because it's always coming from the upper tail, right? You can form the decision rule like this. Reject H naught by looking at this. Reject H naught if T star is greater than T critical or T star is less than negative T critical. So same thing, same decision rule is reworded like this. You don't have to check two things, right? If you form the decision rule like this is like you bind this along this axis, you map everything here to this side, and this is overlapping, right? This is coinciding, right? This particular thing falls here. So you can simply check whether the absolute value, luckily we have got positive here. Even there's a possibility of getting negative. What if this value is greater than this value? In our case, this is 0. But what if this is something else? If we are checking beta 1 with some other hypothesis, right? If this is 5, it's going to be negative and it's going to fall somewhere here, right? So this has a possibility of being negative or positive. How do we form the decision rule? Reject H naught if the absolute value of this is greater than. It's correct to write this one also. It's correct, nothing different, right? This is easy. You just have to check with one value. Okay, so that is how you form the decision rule. If you have forgotten this is how you got this, right? Okay, so what is the decision now? If we draw the T distribution, our critical value is what? This one, 2.306. Our calculated value is 8 point something, so it falls somewhere here. Absolute value of this, okay? So this is basically absolute value of T star. It's 8.5288, right? So what is visible? As our decision, you have to write decision, okay? Reject H naught, or you can say H naught is rejected. You always have to give the significance level with 5% level of significance. How do you write the conclusion? So conclusion and the decision are two different things. When you're doing the hypothesis test, you must write the hypothesis. You must write the test statistic value and calculated value. You must write the critical value. Thereafter, you must form the decision rule. You have to mention this. Marks are given. You have to form the decision based on this. And finally, you have to interpret where any non-statistician can understand. So this one is not comprehensible by a non-statistician, right? So what is your conclusion? I'll quickly erase it and write. This is the end. So it's very important not to use any technical term in forming the conclusion or the interpretation, right? It must be in plain language. Plain language, remember that. Conclusion is what? Take it from the question itself, right? There exists a significant linear relationship between number of ampules. You just repeat the question just like that. It's easy. Broken and number of times the cartoons was transferred from one aircraft to another over the shipment route. So this is like writing a paragraph. You don't have to write paragraphs and essays here. Just 1 or 2 sentences is enough, right? You don't mention any significance level or anything in this conclusion, but you must mention it here, right? So how did you write this? You rejected H0, which means this is the one that is accepted, which means in the population, this model really exists, right? Beta 1 has some value which is different from 0, which means this model is significant for the population, right? So what is the problem context? How did we write this conclusion? They're asking to test whether this thing happens. So what I did was I said yes or no to this, right? Whether there is a relationship or whether there's no relationship. So what I wrote was there exists a linear relationship between number of ampules broken and the number of times of the cartoons which transfers from one aircraft to another over the shipment route. So what if H0 is not rejected? If H0 is accepted, we should say there is no linear relationship, blah, 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 up to here. Okay, it's easy to repeat the question as it is, but make sure you make a clear statement. It should be clear. So this is the test statement. You have to say yes or no to this. Test whether this happens, yes or no, right? So that is how you write the conclusion. I just copy pasted this thing here so you can simply say there exists or there is. You can simply repeat this just because we accepted H1. If we accepted H0, you just have to say no instead of there is no linear relationship up to here. Okay, so I hope this is understood, and this is the end of today's lecture. Most probably I might not have lectures in the next week. I am hoping to have the week off for my for a personal appointment. So I will let you all know regarding next week's lecture somewhere within or right after this weekend, most probably on Monday or at least on Sunday. So I'll put a notice in the LMS. So you check LMS before attending the lecture. I might not have, most probably. So if I didn't have the lectures next week, please come to the lectures on time week after. Otherwise, we are going to have the lecture in case if I didn't tell you anything. So I'll clearly mention that in the LMS. So check LMS before coming. So that's all for today. Thank you very much for participating. If you don't have any questions, you can leave. Otherwise, you can stay and ask questions. Thank you and stay safe.